welcome everyone to this session, which is basically an intersection of mathematics and Python, right? So we'll start with linear programming. We'll try to delve into the basic problems that we have in linear programming, and try to frame the solutions using the PuLP framework. Very basic examples. But obviously, there is no end to this. Things can get complex. You have different solutions for them within the package, which you can leverage at a later point. But this should get you started to explore the piece at least. Okay, so we'll start with three basic things over here. And funnily, I have found a lot of three correlations in this presentation. So just a moment. Okay. So few things we are going to cover here. We'll get into the basics of optimization for supply chain. We'll get into a little bit of, if we may call it a crash course of linear programming, and then getting into the introduction to PuLP and more supply chain use cases, right? So I don't want to delve into a lot of mathematics, then it will take away the whole linear programming vibe from this. So yeah, supply chain optimization. As there would be supply chain experts in this room as well, we all know that when we are doing supply chain optimizations, it's basically an adjustment. It's an adjustment to tweak the values to get into the optimization mode, right? So that you can do cost optimization. You can get into savings. You can solve your even the basic traveling salesman problems to solve miles, which has a great impact in sustainability if you correlate it with the GHG emissions, right? So all the things linked together, it has massive applications. Now, we basically break it down to three things, right? As I was talking about the three correlations. So we have supply chain design, supply chain planning, and supply chain execution. Let's basically understand in few keywords what these are. Supply chain design is basically your supply network design. Where are you getting the raw material supply from, right? That is your supply network design. Then we get into the supply chain planning part, where you have the entire deployment plan. You have your inventory planning. That means when I'm deploying my supply chain, where is the stuff coming from? What I'm keeping on the shelf, right, in the inventory. I'm buying some equipment. Few parts are critical parts, so I need to have backup of those parts. All of these are linked to this whole inventory planning, which is very complex. So in a company which operates in, say, 100 countries, they might be having plants in different locations, and different plants will have different equipment. So you can understand the complexity of inventory as well, right? Now, this whole MRO thing where you talk about parts has a humongous inventory, right? You will deal with a number of suppliers where you will have to optimize their inventory. There is no choice because you will try to go lean on the inventory, but you would also have to make sure that your plant doesn't get stopped due to the unavailability of the part, right? That's where optimization comes into the picture, right? Then coming into the supply chain execution, where you have warehouse, you have inventory management and transportation, which are, again, you can say that there are use cases in every part using LPP or linear programming. Now, coming to the next slide, again, a three correlation. I'm not sure what happened to the N at the end, but I think you get the drift. So design, planning, and execution, these are the three main parts, right? This is what I was talking about. Supply chain design, supply chain planning, supply chain execution. Again, if you take supply chain optimization, you can, on today's day, people use a lot of upcoming technologies, various parts of AI, blockchain, pieces of IoT where you basically can do predictive maintenance even on your plants. So every piece of this, and then the supply chain design, as I was speaking about, is the supply network design, right? Which defines the location of a warehouse, where your raw materials are coming from, all of that. Then the planning piece, and at the last, the execution piece. In the execution piece where you'll have your warehouse inventory management, you'll have your OMS systems, you'll have your trade management, all of that falls into the execution part. Then in between that, there is planning, right? So you do your inventory planning, you do optimization of delivery of goods. That's a transportation problem for you, which you can very well solve with LPP. It has applications in all the 3 zones. That's what I'm trying to call out, okay? So that's mostly the 3 zones that we'll be focusing on. We'll take up some examples, maybe a manufacturing problem where we talk about furnitures, and we are going to get into another problem where it's a bakery problem where we are basically baking cakes, and how can we optimize those things, right? So moving to the next piece, where we talk about 3 things predominantly when we come to linear programming. So linear programming, again, has, like, if you divide these type of areas, the optimization areas, there are basically 3 things again. So you start with linear programming, then you have integer programming, then you have mixed integer programming, right? All the 3 types. So here, when you have your continuous variables, that is known as linear programming. Now, linear programming usually has 3 things. So one is a decision variable, where you basically say what you can control, right? In this optimization space, we call it controlling the controllables, right? First control the controllables, what you can control, and then move to the other pieces. Then you have an objective function, which is nothing but a mathematical expression, right? Which talks about what do I want to optimize. Is it the profit? Then I want to maximize it, right? If it's a specific time or failures, then I'd like to minimize it, right? Depending on that situation, you can do the maximization or the minimization. And the PuLP framework or any optimization model per se gives you options of maximizing and minimizing both. There are very, like I'd say, very sound models available today, because this is not new, right? People had been using Cplex, people had been using Groby. There are Excel solvers available for LPP problems as well. But PuLP can bring it all together. That's the advantage of PuLP. Where PuLP stands apart is it's basically a solver, right, for models. It's not exactly, like it will ultimately call a model and solve it, right? That's how it works. So you frame up all these 3 things. I haven't spoken about constraints, sorry for that. So constraints is again another mathematical expression where you talk about what limits your solution, right? Say you have an inventory problem where you have 400 floor hours. You cannot go more than 400 hours. You have a production problem. Within 400 hours, you will have to solve it. So those type of things are called constraints. So you can see what I've mentioned in the notes. It can be physical, economic, technological, legal, ethical, these type of restrictions, any sort of restrictions. And generally in continuous variables, when you see, you will definitely have, whoever has done LPP problems before would know x1 greater than equal to 0 and x2 greater than equal to 0. That calls it as continuous variables, right? It has no end to it. Now, this is the main thing. Whenever we get into a LPP or we try to solve a linear programming problem, we'll have decision variables, objective function, and constraints. These are the 3 things we need to focus. Now, we'll first get into a mathematical problem. We'll try to see how we frame the linear programming problem. What is the LPP in mathematical terms? And then we'll take another problem where we'll try to solve it using PuLP. Okay, that's what we are going to do here. Now, moving to the next slide, why is linear programming important? So there are 3 things. It can provide you precise results. It has a lot of practical applications, and it's relatively fast because you have an option to choose the models as well. You can select that I'm going to use Groby, or I'm going to use Cplex, or I'm going to use something else. So all of those are available. So again, I think another thing which is important is linear programming is something that is hugely applicable in industries like food and agriculture, engineering, transportation, manufacturing, and energy. I have use cases, I've outlined use cases for every industry, which I'll share with you at the end of the lecture, right? So we'll have some slides on those too. Moving to the next one, this is what we call a classic furniture problem. Like this is, there is a book called Supply Chain Analytics. I have given the notes at the back of this material as well, written by somebody from XLRI, where you have this problem, and they have shown how to solve this. So this is not a new problem. This is a very old problem. So let's go through it. And it really gets complex, okay? We are just breaking it down. So we are trying to get into optimal production. So a furniture manufacturer wants to produce two products, chairs and tables. Available resources are wood and man hours, right, of labor with the following levels. Resource level of wood, you have 400 cubic feet of wood, and you have 450 man hours available, right? Just like how many hours you might have on the floor, production floor. So now to produce one chair, it requires 5 cubic feet of wood and 10 man hours. Whereas to produce a chair, you need 20 cubic feet of wood and 15 man hours. Profit of a chair is $450. Profit of a table is $800. The objective is for the manufacturer is to use all of this, what you have, right? The 400 cubic feet of wood, 450 man hours available, and optimize your profit by making chairs and tables and selling those, right? So now how do you do it? So firstly, let's go back. Let's see the three pieces that we had. Decision variables, objective function, and constraints, right? So we are going to frame these three. Let's start with the decision variables, okay? So the decision variables part, we have considered x1 number of chairs or x2 number of tables. So the objective function obviously becomes 450x1 plus 800x2. Let's go back and see what the problem was. You can correlate, right? The profit. That's what we are trying to maximize. Now, resource constraints, 5x1 plus 20x2 less than equal to 400. The reason being that you will have to use 5 cubic feet of wood and 10 man hours for one chair, right? And you have 400 cubic feet of wood, right? And you have 450 man hours. So you basically take 5 and 20. That 5 and 20 x1, 5x1 plus 20x2 cannot exceed 400, and 10x1 plus 15x2 cannot exceed 450, right? That's what we are doing here. That's what you have in the equations. So that is your resource constraint, right? And getting into the, you have defined your resource constraints. You see both constraints are linear, right? Or you can say that these are continuous. X1 and X2 are continuous variables, right? It can be 0 as well. I might produce no chairs because my objective is to maximize profit. It's not that I have to produce one chair at least, right? So the problem can be represented as maximize 450x1 plus 800x2, which is nothing but my objective function, right? Which is right here. So I'm maximizing this. Now, that is subject to what? That is subject to the two constraints that I have defined, along with what I talked about, right? X1 and X2 can be equal or greater than 0. So this is the entire LPP problem. You have formed the LPP, right? For some of us in the room, it must have refreshed memories, right? So for me as well. So when I was preparing for this, I was remembering the classes that I had taken on LPP. So it's very interesting. Now, getting into how do you solve this? Now, I'm not going to solve this here. This is generally, for this one, you have an answer of, like you have to plot these two lines. Where it intersects is generally your answer, where you have the answer to this is 24 and 14. If you put 24 and 14 in X1 and X2, you will see the optimal utilization of this 400 and 450. It equates it. So that's why That is but that is how you form it, right? Now, if I have formed it, so what? Can I use it? My job is not to get into pen and paper or Excel and solve it, right? I want to obviously automate the whole solution. How do I do that? We'll use something like PuLP to break all the things down. We'll start with decision variables, objective function, constraints, break down each part, and then form the entire problem. Let's see how we can do that, okay? Now, PuLP. Before going there, let's introduce you to PuLP. Now, PuLP, like the other ones that you see, like the other ones that you see over here, Ciplex, Coin, Gurobi, or maybe your Excel solver even, where you basically you can have a model to solve it. But this guy, PuLP, this package is not a model. It's a model solver, right? So you can frame your problem, you can frame your LPP like we did just here, right? In Python, of course. And then you can ask the package to solve it for you, right? You can go for, there is a function called model.solve. Using that, you can, unless you give any option that I want to select Ciplex, Coin, or Gurobi, it will do it, it will find that solution on its own and go about it. But if you want to provide inputs that I want PuLP to use Ciplex, I can even force it to use Ciplex, or I can even force it to use the other models that you have, right? So getting into the next part, where we talk about the resource scheduling problem, right? Where we are trying to maximize the profit. Now, when we are trying to maximize the profit, we are talking about a bakery which sells 2 types of cakes, right? So, and the resource constraints, there is one oven, there are 2 bakers available, there is one packer who only works 22 days of a month, and there is time constraint. You have to do this in 30 days, right? So again, we are putting the time constraint. You have the resources available, 2 bakers, 1 packer, and 1 oven, and you have to optimize how many cakes you will bake so that you have maximum profit, right? So you can see that cake A takes 0.5 days of the oven, and cake B takes 1 day. Similarly for the bakers and packers. The bakers would use 1 day or 2.5 days for the 2 types of cakes. Packers, similar, 1 day and 2 days. So cake B is obviously the one which requires higher resources, right? And then try to get into, these are my profit ratios. Like obviously, cake B, when you are trying to prepare a cake which requires more resources, it's giving you more profit as well. But the other one, where you take half of the things, basically, half of the resources, it gives you smaller profit, which is, again, the numbers are also double of each other, right? So now how do we do this, right? What are my decision variables? A and B, just cake B, we call it A and B, okay? Now, coming to the objective function, you have already seen that the profit for the first one was 20, profit for the second one was about 40. Right? So we are framing 20A plus 40B. And we need to maximize it because it's profit, right? Coming to the constraints, we have these in the table, 0.5 plus 1 day, where 1 day, then again, bakers 1 day, 2.5, and packers 1 day and 2 days. So that has been put into constraints, right? And you have A greater than 0, B greater than 0, same theory, that I might choose to produce cake A or cake B, right? Or not produce it even, right? I might end up in producing 0 cakes. That's also possible, right? Now, how do we go ahead and solve this, okay? So just give me 1 second. So in terms of resource scheduling, the modeling process in PuLP actually in general, the modeling process in PuLP will take these 5 steps, be it a resource scheduling problem or anything. So you'll have to initialize the model, you will define the decision variables, you'll define the objective function, you'll define constraints, and solve the model finally. And this model, you can also say that I'm going to use Ciplex to solve it or Gurobi to solve it. Now, how do you initialize the model, right? So you have this LP problem, right? LP problem is the function where you can have, like, no name is, of course, a name, but the point is you can provide a name of the model, and you can put it to minimize or maximize. The sense is LP minimize in here, right? Because we have taken the minimize part, you can always choose to change it to maximize. By default, it will be minimized. So if you are doing LP minimize, you don't have to even mention it. You can just play with LP problem name equal to something, right? You can get started. So name defines the final .lp file when you produce the linear programming problem in a file. Then you have the sense parameter, which is either minimize or maximize, like profit or failures, right? One you will maximize, one you will minimize. Like delivery time should be LP minimize and profit should be LP maximize, right? Now it returns an LP problem. Understand this, that it will return a .lp file, it will be the problem. And then you will feed that problem into the solver, right? That's the whole motto. So we have imported PuLP. This is the whole code. So you have imported PuLP, then you're initializing the class. We are just calling it maximizing bakery profit, and we need to maximize the profit, right? So that's why we are using LP maximize, sorry. So that's the crux of it. Then getting into the decision variables. What are my decision variables, right? So the general syntax is you go for LP variable, you go for low bound, upper bound, you define the category, continuous, integer. So here what we have done, you can just go through these very quickly. The name is obviously the output. Then you have low bound, variables range, upper bound, and again the upper range. Then this can be a linear one, then it will be continuous, or it can be integer or binary as well. So there are options, right? So what we have done here is, if you look into the problem where we were basically trying to we are having A greater than equal to 0 and B greater than equal to 0. That's why our lower bounds are 0. And the categories have been put into integer, right? So this is the decision variable part where I have defined A and B. Going to the next piece where we have the objective function. Since we have defined A and B, the next thing is getting into the model, basically. So we are adding it to the model that this is my objective function. PuLP is intelligent enough to identify this will be your objective function. And we are defining it as 20A plus 40B. Then coming to the constraints, you have seen this table. I don't have to tell you that these were the constraints. That's how we defined it, right? So that's how we are defining it here too. That's what you have here. We are adding 0.5a plus 1b less than equal to 30 and the others, right? Because last one is for, remember there was a packer who could have only worked 22 days. That's why 22. And then we get into model solve, right? Then produce kk, then you just provide the value, and this will give you the result, right? This is the entire thing, but within the model solve, you can also make sure that PuLP is using a model of your choice. You can define this will go to Ciplex or Coin or Gurobi. That you can do. Otherwise, it will choose on its own, right? So moving to, now this is mostly what I wanted to cover. This is the syntactical part, how we can put a mathematical problem into this shape and form in Python and finally solve it, right? Now we'll start getting into the use cases. What are the industry applications? in which industry, what are the optimization use cases where you can start using LPP, right? It could be integer programming as well. If it's integer programming, you can also do that in a similar manner, right? Now, getting into, this is the whole code, okay? We're starting with the importing of the PuLP framework to initializing the model, defining decision variables, objective function constraints, and solving it. This is the entire thing. True, but true, it could be, but we need to understand that we cannot produce half cakes. So was the other case as well. I couldn't have produced half chairs. So we are talking about the variable over here, right? We are talking about because unless you produce the entire cake, you don't get the profit anyway, right? So that's how, in terms of continuous variable, what it's meant is these are all, like you have a greater than equal to 0 sign, basically, which means that it can start from 0 and keep on going. If I change these values over here, where I have my lower bounds and upper bounds, which keep on going up, it will change it, right? In integer problems, usually, there will be an integer assigned to it that I am going to produce, like, say, chairs and tables. I'll have 5 chairs, and the tables could be anything, right? Then it's either a mixed or an integer problem. That's how it changes. So, going to the food, and I hope I was able to answer that, right? Yeah. Will the result into integer output for A and B, or will it also result like 3.5 and 7.2? No, it will give you the results which are actually, because we have given it straight questions, right? So it's going to plot those 2 lines and give you an intersecting point, which cannot be decimal. So it will be full numbers. But the point is, if I take a step back, what we had been basically doing is there are other things in here where you say that I was going through another problem when I was preparing for this. There was a gym problem, right? How many push-ups you do and how many minutes of running you do. So the answer to that one in particular was you don't have to do any running. You can only do push-ups. So that means that one will become 0, right? So it's just like that there are options to produce nothing as well. It could be, depending on when you are trying to burn maximum calories or you are trying to gain maximum profit. It can always become 0, right? So I'll get into the industry use cases where you have massive applications, right? Especially if you look into the supply chain piece, you have massive applications. What I haven't covered? Now, where it can get complex. This is a very simple example. Now, tomorrow you say the decision variables are more than 2. We have just seen 2, right? There can be n number of decision variables. How do I solve that? So then we use something called the LP sum. There is something called LP sum within the PuLP framework, which you can use to bring in a lot of decision variables together and frame your objective function in such a way that it will cater to that problem, right? I haven't covered that piece. And there are other things as well. We have just touched upon production problems, resource scheduling problems, but there are other applications. You can say that something like a traveling salesman problem, an assignment problem. These all fall into this category, which you can basically solve using the same mechanism. But all are applicable to supply chain use cases, right? Now we start with the food and agriculture piece, where we say that by what we can do here is we can basically determine what crops they should grow to maximize profit. Again, so whether I should grow X amounts of carrot and Y amounts of beetroot that I can project, right? And then the quantity of it, how to use it efficiently, all of these can be a part of it. And the constraints. The constraints are, you'll be able to relate to it. You have dietary guidelines, nutrient guidance, and then cultural acceptability, right? These can all be the constraints in that space. Going into the other part where we talk about the transportation optimization, and this is a critical area where we try to, obviously, in the world we live in, we cannot live without transportation optimization, right? So even when we are chasing our sustainability goals, right, we'll have to do transportation optimization. There is no choice, right? So that's where it has tremendous applicability. And then you can do scheduling, travel time, etc. What will be the load? Again, when you, especially in supply chain, when you have vehicles which are shipping raw materials or sending raw materials from point X to point Y, you will need to understand the load the vehicles can take as well, right? Is it a vehicle which takes X load or Y load? Based on that, your whole problem changes. No two vehicles are same. That's how it's defined. There could be X number of similar vehicles which can carry 20 kg or Y number of other vehicles which can carry 50 kg. So how do you balance that out? So that is another thing, and it always adds into the problem that we are trying to define, right? Now, going to the next piece where we talk about plant management, right? I think I covered all parts of it. Yes, mostly. So all types of modes, you can bring this to all types of modes. Then you have logistics planning. You can schedule workers like we are scheduling bakers and packers in the last one, right? Then production schedule optimization. This is a huge use case where you define which production worker should be present at the plant when, right? You basically give them their schedule and make sure that at the end of the month, I have produced the optimized set of products that I could have and gained the maximum profit. Based on that, you basically optimize the schedule, right? So I'm going to need more workers in, say, a particular part of the plant. So I define it in that way. Preventive maintenance. What is preventive maintenance? Preventive maintenance takes in a lot of input from the sensors, right? You have huge equipments. Say, you have a plant where specifically a specific application to CNG, where you have a plant, a downstream plant, where you have a blast furnace, right? Within that, you are getting coking deposits, right? If that thing is happening, it can take your whole plant down. You will not have that blast furnace up and running, and you will have a couple of days to break that coke down, and then you'll have to start it all over again. Can you predict when it will happen? And then predict that downtime, so you do a scheduled maintenance. That is the whole goal over here in predictive maintenance. By basically looking into the use cases when it has failed before. What was the load at that point in time? Defining those variables, first, you'll need a lot of documentation. I remember doing this for one of the plants in the Middle East. So where the main problem was around that there is a blast furnace and there is coking that gets formed, and this layer you'll have to break every 3 months, 2.5 months. They don't know when it will happen. They didn't have a clue. So there were sensors from which we used to get a lot of data. We took all those inputs and then basically frame out when it might happen again. And based on that, they used to take scheduled downtime, right? So that is how it's supposed to work in plant management as well. Yeah. But unless you classify, if you do not solve the predictive maintenance use case, how do you know you have optimized your optimized the resources that you have? You have plant resources, right? X number of plant resources. One resource goes down without the predictive maintenance. You have predicted the maintenance, you have solved, say, 2 days of production time. If you solve that, you are basically optimizing your production. You are absolutely right. It has ML parts to it as well, but it overlaps. That's what it is.
Getting the output from ML, you are doing the optimization for the plant unit.
Yes, exactly. So Manufacturing, in manufacturing, you can get into raw materials, which must pass through various machines. Again, the same in assembly line, the production flow type of thing, right? You can maximize profit, and you can get into the amounts of products that can get affected, how to maximize profit of that, what materials are needed. I have seen situations where a customer who is building an iron pellet, right? Generally, iron is always into, there will be iron pellets which will get created, and post that they will try to find out where my materials are lying and what can be the optimized constituents of this pellet, right? So if I'm getting X type of this, Y type of this, what is the optimized mixture? So there is a lot of like this chemical mixture type of thing that they optimize as well. Then they create the pellets, and based on that, they optimize the profit. So going to the next piece where we talk about the energy industry. Now, energy industry, in terms of grid systems, we have the shortest distance between generation of electricity and demand over time. So that is another thing, right? Just like when you do supply chain network planning, you put a location close to every available resources that you need for the plant to operate, is the same thing over here too. Getting into the last legs of the presentation, you have chemical engineering as well, where you can do inventory control, product mix optimization. This is what I was talking about, the product mix optimization. This is another thing. Process control and optimization can be solved by linear programming. So these, when I show them as use cases, there can be linear programming applications to solve these. That's why they have been put in here. Let's get into, yeah. These are some references that you can use to learn more. There is obviously a lot of documentation available because this is pretty matured, right? People use it in various forms, but this is what you can use. Then moving in, that's where I'd like to close the presentation, but we can take questions because we have quite some time. Yes.
The first use case of the food and agriculture, how do you convert the guidelines into
Guidelines? What guidelines you mean?
You mentioned that the constraints of the various guidelines. Can you go to that slide?
Yeah.
Yeah.
Okay.
So the dietary guidelines and nutrient guidelines, how do you convert them into mathematical constraints?
So say it's a animal feed, right? That you need to then you need to provide, right? So in that, the dietary guideline says that animal, like probably it's an say it's a you're breeding oxes, right? So if that is the case, for them, what will be the optimized thing? How much fiber, how much glucose should get into the nutrients, which is exactly a linear problem. That's how you define it, right? You take the guidelines, put them into an equation, and that becomes your constraint, basically. Yes.
Reinforcement learning is also being used to solve the scheduling problem based on some agent-based learning. So how do you see it is different than what we do over here?
So I'd say this is the crux of it. The reinforcement problem is for this, you'd see that this is pure mathematics where you're applying it to solve it, right? But the ultimate results, you see that there are some applications of reinforcement learning I can bring in at a later point to further optimize this. Then you can think of those parts, but you'll have to start here at least. Then you can bring that in as a top-up layer at a later point.
Okay. Thank you.
Hey, just a quick question. In your experience for inventory optimization, have you seen this being applied when you have so many decision variables? And I'm guessing that's hard as well, right? So.
No, in case of, see, when you start, like there has to be some business aspects to it. So it cannot only be like I need X of this, Y of this. Given the experience, the plant manager can tell you that historically we have stored these amounts of this and we have seen great results. Then you take those inputs and try to optimize it. It's not that I have X equipments and I need X nuts in there as
Finished goods side, right?
I'm sorry?
Finished goods side or in, let's say, spare parts planning anywhere else, have you seen for inventory optimization linear programming being used?
Yes.
Or have you? Okay.
Yes. Because of the reason that, say, you need to go by the guidelines, like the guidelines we discussed about food and agriculture. The equipments also come with guidelines that you need to have these as parts, right? So X machine requires Y such parts as backups. Otherwise, there can be a fault, right? Think about the same problem that if you have 1,000 nodes in a Hadoop server, it has a failure rate of in 3 years, one hard disk fails, right? So you have to keep that storage with you always, right? Otherwise, that server will be down.
Hi, this is Nayan. Actually, first two problem, whatever you showed there, I think objective functions and constraint we can define easily. But when real-time problem comes, so I have seen a lot of challenge to define the objective function and constraint. So normally, what is a regular practice you people are following?
So in that case, that's why I was saying that this was this will get you started, right? This talks about when you have an objective function where you have just couple of things, couple of variables, decision variables, A and B, chair and tables, right? But that can be more, right? So that's where you use advanced techniques, where you have a lot of advanced techniques within this package even, right? Within Cplex, within Gurobi as well, where to define it, you can get into various modes where you start putting it within a vector, all the portions, and then define it using something called LP sum, which is available within PuLP, but you have different options within Cplex and Gurobi as well.
Mm-hmm. So, but I'm specifically, let me ask, like for example, in engineering, suppose whatever the turbine we are designing, so the angle and the number of blade, those things we have to optimize in terms of weight and in terms of performance. So, like here we know, okay, number of chair and all those things, and then we can do.
Yep.
So, can we build a regression model and use that regression equations as a objective functions, and then constraint we know about angle and number of blade and all those things maybe. But my question is, can we use a regression equation as a objective functions in those cases?
In that case, it could be a little trial and error, man. It's not that easy, right? Because what you are talking about is it doesn't give you the fixed numbers, right? We are talking about, I don't actually know how much it should be. Right? So in that case, you can obviously start feeding it, see what are the optimized results, observe it over time, and if it clicks for your industry, for that material, then you use it. Mm-hmm. So there has to be a little bit of trial and error. It's not very, I'd say, it can be done at one go.
Okay. No, but my point is, if we do the regression equation and fit as a objective function, are we not fixing problem as a linear regression instead of optimization? Because whatever the regression model line we have defined, so it will find solution within that area only, correct?
It will find the solution in that area only. You are spot on. But see, then different challenges come in. It's not actually how you get outputs of the regression model. All of that you might not be able to use it, and a regression model might give you multiple solutions, right? So all of those might not exactly fit into it. That's why I'm saying that there has to be a little bit of trial and error in terms of defining the objective function.
Okay. Okay, thank you.